what you can see is a video on a typical additive manufacturing process where layers of powder are put one above the other. So typically between 8 microns and 20 microns is the thickness of the layer, so layer by layer. And then the laser actually scans the surface, and the process is called selective laser melting because the laser goes to points selectively, which obviously correspond to the build. The rest is the part is built vertically. So the powder beds goes down after each layer is applied. So this is the process, very simple process, but actually very, very simple to explain, but very difficult to control the processes. For us, additive manufacturing is something we've been doing since mid-90s, where we started working with plastics, mainly nylon and other materials like this. 5 years ago, we bought this machine, a Renishaw machine, and started experimenting with new materials. We bought equipment for mixing powder, and this actually provides us with the opportunity to study different aspects related to the process itself, selective laser melting. So synthesis of new metallic composites, post-processing, verifying the physical component which is built, looking at damages. I mean, the process is not very well understood. There is porosity and micro cracks. And probably the most challenging aspect is modeling and prediction. So we have built this program of activities in this area, additive manufacturing research, which starts with materials, then looks at functional geometries, and a lot of work is concentrated around process improvement. So see that most of the work in this area is with the manufacturer of that machine. And the other two areas are dominated by working with end users. So one of the first projects we did in this area was with titanium 6-4, alloy used in aerospace, medical and dental industries. The problem is that these industries have very high standards for particle size and particle distribution. So the question the manufacturer wanted to know was how many times the powder can be recycled. So it was just a very well-structured experiment where we were building parts, then removing the extra powder, using it again to build the same geometry, and testing again. And we found that the manufacturer can reuse powder more than 5 times without any compromise with the quality of the part. So that was a breakthrough which allowed the manufacturer to actually build an internal recycling system within the machine. So it's a simple project with impact. And the impact is not only for the manufacturer, but also for all those end users who want to use the technology, but find it a little bit too expensive at the moment. And then we started looking at new metal matrix nanocomposites, where we started mixing a core material as a matrix with additional components. So there is a lot of work trying to determine the most suitable combinations. And for example, with Airbus, I have a project where we're looking at replacing the current tooling they use in the production of wings, tooling which is very, very heavy, not very ergonomic. So they want to replace the tooling with aluminium material, but it needs to be durable and wearable. So this is our ambition. So in general, projects on nanocomposites go through these stages. We study the material, we try to find different recipes, then we melt, and we study the microstructure and the mechanical properties. And we have a very well equipped nanometrology labs for that purpose. We also have a group looking at surface improvement, because this is one of the problems with additive manufacturing. Although people say that you can produce near net components, in some cases the quality of the final component is not good enough to be deployed immediately in production. So laser machining, for example, is used to improve the surface quality. I'm very proud with this research. It's under my supervision, but mainly done by other colleagues. Multi-physics modeling of these processes. As I said, this is a big challenge. The ability to simulate and be able to predict how the melt pool will develop, whether defects may occur. I mean, in some cases, small defects are okay. And to be able to predict the quality of the final part, this is a key research area. So in this example, you can see experiments with this different laser power with different hatching spaces. So different modes of operation, different parameters. But more interesting research is this one, where we combine, and this paper we just published this paper, where we explore multi-material additive. So if we have one layer of material and then followed by another material, how are they going to react under these interactions with the laser? So this is one of the directions for future work. Before you ask me, is very important direction. Now our machine doesn't allow this multi-material deposition, so for that we use other rigs. On the practical side, this is a big project with NFL and also with manufacturers of helmets for sports and for sports mainly. So here we combine our expertise in medical engineering and head injuries and additive manufacturing, and explore different configurations and the impact. And again, this is another direction of research. One of the projects which was actually funded by a student. We experimented with different structures. So this is the ability to absorb shock in one direction differently from impact in the other directions. So we're experimenting with different lattice structures. And this is quite new. This is something I do with, and I supervise a student from China. It's a collaboration with Chongqing University. And again, we just published this paper. So this structure is used in implants. So these are porous scaffolds fabricated by selective laser melting. So they're so imaginative, these students from China. They come back with different structures, different lattices. So we do simulations with them and physical experiments. And it's probably another area of interest to us. The manufacturer was very much interested in process control, as I said. So what's interesting is that many of the additive manufacturing machines don't have internal feedback control. And not many sensors inside the process. And the whole point of the simulations is to try to understand the process, what's happening, and you can't visualize and monitor it very, very clearly. So this is a project where we looked at different controls and different level, the process foundation, settings. In process control is extremely difficult. So we're trying to do some work there, but at the moment, limited success. But this project here looked at post-process monitoring. So we are building different parts, different positioning in the machine with different orientation, measuring deviation, and trying to understand the link between the process foundation and the process settings and the post-process quality of the parts, trying to avoid the sensors inside. And finally, this is also active research at the moment. We're using machine learning to understand the process, again, as a black box process. So here we have the process parameters. These are the mechanical engineering properties. If we manufacture lots of parts, maybe machine learning will enable us to find some correlations. So this is a project funded by the European Commission. And finally, I want to thank all my colleagues who I have worked with on these projects. Several PhD students, research associates, academics. So it's a large team, and I have to say thank you to them. So I'm happy to answer your questions. I'm going to stop. I did stop the sharing. I'm absolutely relieved that the presentation wasn't interrupted, so I could even run the video, which was the bonus. So I'm happy to answer your questions, guys.
Yes, Rossi, thank you very much for your lovely presentation. We enjoy a lot all the information and all the projects that you share. So we will ask in Spanish. Someone wants to ask something, and we will try to translate in case that we need it, and later we will translate in Spanish again in case. Okay.
Okay.
Bueno, quisiéramos preguntar si alguien quisiera intervenir con alguna pregunta, alguna precisión sobre proyectos. Ella está también muy abierta a oportunidades de colaboración, entonces, pues, los escuchamos.
Angelita, ¿puedo yo hacer una pregunta?
Sí, claro.
Okay, Rossi, here in Colombia, we have a problematic industry. As we talked before, we have a huge gap between industry and academia. Maybe you can tell us some advice how we can convince as a researchers the industry to finance our projects or to get involved more in researching?
Okay, so you'll be surprised to hear that this is a big challenge for us as well. Especially if you want them to fund basic research, okay? So this is a big problem because they're very quick to fund, for example, sometimes a PhD student. But the problem is that very often they want to influence the direction of that PhD. So you end up with the PhD student having pressures from the company to work on their coding or their, I don't know, experiments, which are not terribly scientific. So there is always distraction between academic research and what industry understands and can directly apply. So for me, the main breakthrough for me was when I finally understood the technology readiness levels, the concept of TRLs. Are you familiar with technology readiness levels? No? Okay, so this is something which I think was introduced by, was it NATO or, no, not NASA. It was introduced by NASA many, many years ago. And it's a way of measuring the maturity of a certain technology from concept to the market. Okay, so you start with technology readiness level 1, where you have proof of concept, and you develop your technology through these 9 stages. And technology readiness level 9 is something ready for the market. Now, when industry talks with universities, they expect that our research is market ready. And I find sometimes difficulty in explaining to them that actually universities are not supposed to produce market ready products or processes, okay? Universities are for producing theories and new concepts and new ideas and testing those. More applied universities and engineering schools have to work on translation science. So there are three main sections in the 9 technology readiness levels. So 1 to 3 is where the novelty is, novel science. So you can publish really strong academic papers if you work in that space. And research councils, they like that science, okay, because there is novelty in it. And it's extremely difficult to convince industry to sponsor that sort of research. Okay, so you need the ability to invest in novel ideas using your own resources, your spare time sometimes, unfortunately. You have to prepare yourself before you become ready to work with industry. Okay, so sometimes the problem is in us, because we can't explain clearly where the benefits for them are in the research we're doing. So technology readiness level 4 to 6 is where you have to develop that proof of concept into a demonstrator or prototype. Okay, so this is what we do to convince them to fund us, okay, or work with us. We need to show them a working prototype or demonstration or simulation. This is what convinces them, or case study. Okay, so this is how you have to convince them. And I'm lucky because I have funding for basic research in robotics, by the way, not in additive. And I have funding for applied research in additive. So I sort of understand the difference in what we do. So some of the funding for applied research can be used to experiment with new ideas. So they want you to concentrate on a specific benefit for them, like Airbus. All they are interested at the moment are weight reduction. They want to make the tooling a little bit lighter, okay? And then we do the job for them, we demonstrate, and then we say, however, we can try to improve the mechanical properties and further reduce the weight by exploring some new materials. Are you interested? So they've seen that using new materials, we can give them the benefits immediately, and then we can start discussing with them a more basic research projects, with something we haven't tried and is a bit risky. So it's a complex conversation. So you need that understanding, and you need to explain to them what is possible and what is not possible, so they don't have big expectations, you know.
Thank you, Rossi. I think it's a good advice. Thank you.
We have some questions here in the chat, so I will start to try to ask some of them. There is one that is related more about what do you think, or what do you have in mind, or what do you consider when you are going to test a new material in those processes that you show us.
Sorry, say again. When we start testing new materials,
what do you consider? What do you have like in consideration when you are going to try a new material in a process, or maybe a new process or something like this? So, yeah. Which are like the main ideas that someone has to consider in that case?
I think the main idea is really what's needed. Okay, so if and also can you make in additive, the main problem is that additive manufacturing, selective laser melting is suitable for a very selective number of materials. Yes. So to be able to expand the applications, we need to look at which materials are not possible to melt, to produce this way at the moment, and can we improve that situation? And the typical example is our work with aluminium, with titanium, with nickel. So what the starting point is looking at the chemical composition of the alloys, trying to preserve those components which are needed in the composition, and in most cases, maybe this is not correct. In most cases, we start from failure, actually, very often. So aluminium 2024 is very difficult to manufacture using additive manufacturing. Okay, bad results. So the starting point is, can we improve the performance of that material? So we start from failure. We look at what doesn't work, and then we try to improve. And the motivation is that this is a material very broadly used in aerospace and automotive. Can we improve the manufacturability of that material? So the starting point is failure, actually, I would say.
Yes, for many things in
So be
Yeah.
brave, experiment, learn from failure. I think failure is the best advisor.
Rossi, I have a question. I have own question about the project that you were working with titanium. For this, for example, was easier to create like kind of structures or something in the surface. And if you have the opportunity to try some tribology properties or something like this. I'm sorry, I just saw what you produced, and I was amazed because in general, these kind of surfaces are really nice and are really good if you can work with them, for example, for implants or this kind of thing. So
yeah.
It's easier to create these kind of surfaces.
This is where the benefit of additive manufacturing is, because you can implement surfaces which are mathematically possible, but until now were not manageable using traditional manufacturing processes. So this is really the big potential for additive. And you are absolutely right, in medical research and implants, this is the type of research we need. At the moment, we're looking at logical structures, repeatable structures. However, and this is something I'm looking at again with collaborators from China, we're looking at real bones and their structure. And the structure is not homogeneous, okay? The structure of the bones is, you have different density in different directions, different behavior. Can we use machine learning to learn from structures which come from nature? And can we replicate some of those structures? And with additive manufacturing, you can produce almost any structure. The problem is with powder, you need to have exit for the powder which is not melted and solidified after that. Okay, because the process is you melt and it solidifies after that, and the powder which is outside that area will be reused. So this is where the sustainability comes from. Okay, so you only use material which is needed to produce the structure. But the problem is, if you have cavity, okay,
Yeah.
where is this powder going to go? Okay, so there are technological limitations on really small cavities, but hey, this is what research is about.
Yes. Rossi, there is a question about how do you think about the use of polymers and inorganic additives in this kind of, for example, industry, and how they impact the processes in general?
Polymers in additive or
Polymers as the bulk material and inorganic additives. I mean, I think there is like kind of fillers or yeah, some reinforcement.
Yes, yes. There is a lot of research on new materials, and in fact, other additive manufacturing technologies. I only show you selective laser melting, but there are 10 plus more additive layer manufacturing processes based on different physical processes. For example, sintering, okay, is used in polymers. There are 10 plus other processes which can be investigated, and they're more suitable for polymers. I only presented our research on metal because this is high value manufacturing. This is what aerospace and automotive are interested in. So it really depends on the application. I can see a good question here about the accuracy between the simulations and
the kind of software that you
the real. Well, this is what really we're trying to achieve. Good simulations results. A model is never accurate enough if the simulation is not verified by real experiment. So the simulations this is the difficult, the simulations of this multi-material multi-physics, where we monitor, we simulate the molten pool. I mean, the problem is that they're very difficult to verify experimentally, because you can sort of see the molten pool, but the process is so quick that you can't even capture, you can't capture very well the transition. So the way you can verify the simulation is by the final result. Is the prediction of the simulation close to what the physical part at the end of the process is in terms of mechanical properties. So this is the difficulty, that the machine is like a black box. You can't easily put sensors inside, and the simulation of the process inside is difficult to verify. So the verification is by the end product.
Okay, great. Rossi, there is a question also, taking into account the times that we are living, where we have all these new materials that we are consuming, that also we have these new opportunities for new energies. So there is someone interested in to know how these new technologies can contribute to to fight with the warm global.
Okay. I mean, I've spent some time thinking about how sustainable additive manufacturing is, because it consumes a lot of energy, but energy applied in a very focused way. Okay, so the laser beam attacks a particular point. This is where the material is melted. So this is one point in favor of sustainability, that energy is used in a very efficient way. Also, material is used in a very efficient way, because the excess powder is reused essentially. So this is the big difference with subtractive processes, where you mill, for example, components, or you drill holes, you throw the material, and exactly that's why we need this Royal Academy of Engineering project, because we're looking at the recyclability of this excess material, isn't it? So this is the sustainability impact, that can we produce a model of circular economy, where one process, the waste from one process, can be used in another process. So in that respect, I think Adriana's project is very, very much in line with this thinking, benefits to the economy and ecology. Now, I think this is the problem with some of the research which focuses on the environment only. We need technologies which can benefit the economy as well as the environment. So we need productive sustainability in a way, so everyone benefits.
Okay, I think we have a couple of questions more, but it's already 2 p.m. here. So what we will do is the same as last conference. So we will take all the questions, and we will send to Rossi, and later we will publish or send the answers, because there are some about the people that want to start a new business. So there are kind of interested questions. So thank you very much. Yeah.
Can you give me 1 more second?
Yeah, sure.
So for those of you who have ambitions for research, I mean, the funding is always a problem. But if you're looking for a study abroad, fellowship, exchange of staff, we can arrange this. I can host your study if your area of research is of interest to us as well. I can help with that regard. So don't be ambitious. So this is my advice: be ambitious and look for collaborations, and don't be afraid to challenge yourself and your thinking, and start a new business or new research area. So if you need help, I'm happy to try to help. My funding doesn't allow me to spend for certain activities like sponsoring a PhD student, but there are other ways to help. So do let me know.
Thank you very
Thank
much.
you very much for having me, Angela and Adriana and Frankie and all of you. Thank you very much.
Thank you very much. We really enjoyed the lecture. It was a really interesting topic, and thank you very much for being so nice to answer in really detailed way every question.